Hi Scott, Dave here. I've prepared this video to accompany the files, the antenna modeling files that I sent to you. I think this might help if you haven't used these before or seen them before. This might give you an overview of where they come from and what they're doing that might help them be a little more meaningful. I'm going to cover just the antenna modeling part here, and then I'm going to do a separate video similar to this just for the transmission lines. This is the antenna modeling software that I use is EZNEC. There's a lot of information about it on the web. You can look that up if you're interested. It does all the heavy lifting. Actually, there's an algorithm from Lawrence Livermore Labs called NEC2 that's the heart of it. EZNEC is a software wrapper around that makes it a little easier to use. There's another program, actually it's a Excel script called AutoEZ that makes it easier yet. And so that's really this here is the tool that I use to create the wires and feed point connections. There's a lot of other things it can do, and that feeds the information into EZNEC. So I've used this to take the dimensions that you sent to me and model the antenna. We'll look at it visually here in just a minute. It's kind of tough to picture what it looks like just from looking at these numbers. A couple of things to point out here. I have included a dielectric constant for the wire insulation. Here's the dielectric constant of 3.5 and a insulation thickness of 0.022 inches. Those are fairly typical values. That can have an impact on primarily the impedance and resonant point of the antenna. And I'll just take this moment also to say that this is a model. We want to be careful about, even though it has a good reputation, EZNEC has a great reputation for accurate modeling, just have to take it with some caution and realize it is a model. So I think its biggest value is in helping us understand what's happening with our antennas, and then when it gets right down to the detail about exactly what resonant frequency there is or exactly what feed point impedance there is, always best to compare that with actual measurements. But I will say that my experience so far is that the models are very, very close to reality. I'll point out another thing here in the setup. We'll switch to this calculate side. EZNEC has the ability to account for skin effect loss in the wire. We had set that up on the previous page to number 12 per your specifications. And then also, because the RF signal interacts with the ground, and it has a considerable effect, EZNEC has the ability to set the ground type. I have it set here for an average ground. You can see some of these other types that are here. I believe that this, for where you're located, is a reasonable estimate. But again, it's another thing to keep in mind. This can affect the results. In this example that I'm using, we're only going to look at 20 meters. And all the other graphs that I sent to you kind of follow the same format, but for the various bands. So I can enter a series of frequencies. I have these set up from 14 megahertz to 14.5. Obviously, that's a little past the band. I was using it that way because 80 meters had a 500 kilohertz swath, and just made it convenient for me to change this one value up here, and it would fill in the rest. So obviously, the 20 meter band ends at 14.35. I ran the calculation on this, and it produced a number of things. One is what the complex feed point impedance is, And so these two values, here's the column for the resistive value of the complex feed point impedance, and here is the column for the reactive part of the complex impedance. Say at 14.1 megahertz, we see a value here of about, that's almost 239 ohms resistive and minus 573 ohms reactance. That'd be capacitive reactance because it's minus. It also made some gain calculations and SWR. SWR doesn't mean a lot to us right now because that's at the antenna, and we know that the transmission line will dramatically transform these complex impedance values. So we're going to need these values to do the calculations to see what effect the transmission line has, but it's hard to really do anything with them. Let's look at this in graphical form real quick. I mean, we can see that it's not resonant. We know it's not resonant because none of these reactive, at least on 20 meters, it's not resonant because none of these reactive values are 0. But that doesn't really matter. It doesn't change our ability to couple a signal into it or change the ability of the antenna to radiate or pick up a signal, which we'll see more of here in just a minute. So on this page we see the values represented graphically. The red line is the resistive feed point value, and the blue line is the reactive value. And the resistive scales here and the reactive scales there. And you can see that it changes with frequency as you might expect. So this goes from 14 to 14.5. 14.3 is about right here. So let's take a look at these. I'll also mention, here's the SWR. Again, this doesn't really matter to us that much because these impedances will be transformed by the transmission line. And then the gain here, although this is meaningful, there are some easier ways to look at it, which we'll do here in just a minute. Let's take a look next at what the antenna looks like. So on this page here, there's a button to push to view the antenna. I've already done that, and EZNEC has it here. So this is based on your dimensions, and hopefully as you look at this matches what you think it should look like. This is looking straight down on it. In a moment we'll rotate this in three-dimensional space so you can get a sense of what it looks like in that way. Y-axis up here is pointing north, and this is the x-axis is pointing east. You might have to correct me. I presumed, well, I looked at the Google Maps for your QTH, and from your drawing it looked like this line here, this wire 2, might be completely oriented with north, but on Google Maps it looked like this was offset a little bit. So anyway, this is what I've got, and you can, if I've gotten it wrong, you can correct me and we'll fix it up. Or actually, you could just, this looks like what, 5 degrees, a few degrees anyway. You could just, in your head, just rotate some of the directional values that are in the graphs. Okay, so let's also now look at what the modeler produced for the radiation pattern. And I'm going to slide this over here. So this is these two windows are tied to each other, which you'll see in a minute. Actually, you know what? Let me bring this down. I wanted to show this to you in three-dimensional space. Let's rotate this around, and you can see, you can see the height of the thing relative to the ground. From your dimensions, this point which is the feed point, by the way, it was 36 feet high. This is 36 feet high at this point. This one was 45 feet high, I think, and this one was 65. And you can see that reflected in the three-dimensional image of this thing. So let's take it back up to just having it straight up and down, or as close as I can get it here without fiddling too much. That looks good. And we'll bring up that radiation pattern again. So this has been calculated by EZNEC. And what's neat about this is we can rotate this around in three-dimensional space also. Why is this so irregular? Well, it's because of the shape of the loop. If the loop were square or rectangular or symmetrical, a symmetrical triangle of some kind, equilateral triangle, or especially an equilateral triangle, or five-sided polygon, or if the antenna itself had symmetry, this pattern would have symmetry. But because it's asymmetrical, the radiation pattern is asymmetrical. So if I rotate this around, you can kind of see through the wire mesh, the humps and bumps in the thing, and how it relates. You can compare it to the antenna orientation over here. You can see, how it relates. So it's a little hard to look at it this way. Let's get this straight up and down. Fortunately, EZNEC has a couple of additional tools that let us envision this more easily. So let's look at this. This is a slice through the predominant lobe on this. In fact, if I rotate it off to the side here a little bit, you can see that this red line, matches this elevation slice here. So we'll just put this back up, sort of close to bird's eye view, and take a peek at this. So what is this telling us? This is saying that 14.1 megahertz at an elevation angle of 22 degrees above the horizon, we have the peak of the lobe, and it's at 10.33 dBi. So that's compared to an isotropic radiator. A dipole in free space is 2.15 dBi, and the I means this as compared to an isotropic radiator. A dipole over ground, say if this was a 20 meter dipole over ground, broadside to the antenna, we might see the angle would probably be a little higher, might be up here around 30 degrees or so, and say at a height of 35 or 40 feet, and the gain would be, I'm just going to guess here, about 7.5, over an average ground anyway, about 7 or 7.5 dBi. So you've got what? You've got 3 dB or so better performance than a dipole. Actually, it's probably better than that because your main angle is lower. A dipole at this angle might be a full S unit down. So this is a substantial, 20 meters, this is a substantial gain. And the low angle is definitely in your favor. Let's see what else. You can see also that you can see some of the irregularity in the pattern, in these lumps and bumps. And you see on the back side of this, again, part of the asymmetry is that it doesn't have much gain off of that side. So towards Europe, you've got a very strong signal, and my guess is that your experience with this loop has produced some great results to Europe with this. Seems like there was something else I was going to add to this, and it's not coming to mind right now, but maybe it'll come back. Let's look at this. Let's look at this in terms of an azimuth slice. So this is really just the outline we're seeing here. This is for sure the bird's eye view, and it's at that elevation angle, the 22-degree elevation angle. If we change to that 22-degree elevation angle, this pattern would change. But this is the pattern that outlines where the maximum gain occurs. So this outer ring on here is the 10.33 dBi, and then you can subtract down from that. That's true on the elevation graph that we saw a minute ago also. So you can take a peek at that. You've got some lobes here that are pretty nice also, that don't have quite the gain, but they're only a dB or two down from this peak. And at a very low elevation angle, so you might also have some experience with, some good results to JA land, or possibly some areas in Africa or the Antarctic with this lobe here. Definitely a great orientation to Europe here. But you can also see, and this is characteristic of a loop antenna also that's many wavelengths long. You have these deep nulls, so there are going to be azimuth orientations that you're just not going to do very well with. And I guess stateside, even on 20 meters stateside, you'd see good performance to the southeast and to the southwest and the northeast for sure. So you probably have experience with that too. Let's see, is there anything else about this? I think this might cover it here for the radiation pattern and the antenna analysis that way. So you can compare what we've talked about here, all the other graphs, and see how it relates. And then I'll do a separate video for the transmission line. If you have any questions about it, let me know. Hope this was helpful. Thanks.